This is our final video on nuclear energy, and we're just going to look at the fission reactor. We're going to obviously remember we can't do fusion yet, so we're going to focus on fission, look at the main components and some of the jobs that they do, and also some safety features at the end. So a bit of a simple diagram of what's known as a pressurized water reactor, and you can see I wanted to talk through this diagram just so you can see some of the inbuilt safety ideas. Over on the left hand side we've got the reactor. And here we're going to talk a little bit about control rods. So you've got the fuel assemblies where fission's occurring, lots of heat being generated, it heats the water up, and now this water will heat this water, which is which goes to the turbine and a generator, and you can see that they're two separate systems. So the water that is used to heat the water to produce the steam does not mix. So in the event of any problem, the two waters are kept separate. You've just got a heat transfer from the two waters. The reactor is going to be in a steel pressure vessel here. It's going to be surrounded by concrete in a containment structure. So the whole idea is to keep this as safe as you possibly can. Then all of the usual stuff, the turbines, the generators, etc., that can be outside of where the fission is occurring. So a nuclear power station in principle does exactly what a coal-fired or a gas or an oil-fired power station does. It's just the way that the water's heated is different. But all of this equipment on the right hand side would be exactly the same that you have in a fossil fuel power station. Okay, so to do this we need uranium. We've talked a lot about uranium. If you dig uranium up out of the ground, it's not fissile. We would say it's not capable of fission, but it is described as fertile. So if we enrich it, then it will, if you increase the amount of uranium-235, then it will become a fissile material. So enriched uranium is where the percentage of uranium-235 is increased. We do this by centrifugal mass spectrometry. It's used for nuclear fuel, but also weapons. So if your business is enriching uranium, you're going to be watched closely by the International Atomic Energy Authority, because obviously they're going to be keen to make sure that the enriched uranium is used for fuel as opposed to nuclear weapons. So you can see there's some diagrams here. Natural uranium is predominantly 238. Low enriched uranium, reactor grade, is about 4% uranium-235. So you've just got a little bit more uranium-235. Depleted uranium is uranium-238 remaining after enrichment. This is less radioactive. It's got a very long half-life, but it's very dense, so it's quite useful for weapons, shielding, etc. But the problem is it's very hazardous because the bits left over when there's explosions, or if it's exploded, then it's radioactive and it can scatter over a wide area. And you can see here the last pie chart, highly enriched uranium, known as weapons grade uranium, is up to 90% uranium-235. So you can see the difference between reactor grade and weapons grade is very significant. Okay, a little bit of what we need to know about the moderator. Nuclear power stations use fission. Thermal reactors use uranium-235. We've said that by enrichment. But the issue here is that uranium-235 can only absorb fairly low energy neutrons, described as thermal neutrons, and they're called this because they have a similar energy to a nitrogen molecule in the atmosphere. So we need to slow them down because the neutrons released in fission have energies of about 2 mega electron volts. So in order for the fission produced neutrons to be absorbed to go on to cause another fission, we need to slow them down. So to slow them down, we use a moderator, and the moderator is quite a simple idea. The collisions with the moderator nuclei cause the neutrons to lose energy. So we're just going to look at a couple of quick calculations. So first of all, if we estimate the kinetic energy of a nitrogen molecule in the air around you, to do this we're just going to use half mv squared, half the mass of nitrogen 2, and this converts it to kilograms. And in terms of the average speed of the air molecules around us, you might have known some of the other work you've done. We're going to just say it's about the speed of sound, so 340 squared. So we've got an answer of 2.7 times 10 to the 21 minus 21 joules. If we just quickly convert this into electron volts, we get an answer of about 0.02 electron volts. So here we have, if a neutron collides elastically with a stationary carbon-12 nucleus, so carbon's going to be our moderator to slow it down, it can be shown that it loses about a third of its energy. So how many collisions will be required to get a fission neutron, which comes out at about 2 mega electron volts? We need to get it down to about 0.02 electron volts. So it's quite significant. Now you could do this on your calculator. You could start with 2 times 10, 2 mega electron volts here, and you could just go 2/3 times 2/3 times 2/3, and then count the amount of times you press the equal sign and wait for you to get to 0.02. Or you could use a little bit of maths, and what we're saying is that the energy of the neutron when it comes out is this. If we multiply that by 2/3 to an n time, we need to get an answer of 0.02, and so we're trying to solve this for n. Here we can use some logs, can't we? So I've just sorted out the maths first by dividing 0.02 by 2 times 10 to the 6. So work it through, take logs of both sides, so log of 2/3 to the n equals log of 10 to the minus 8. Log of 10 to the minus 8 is minus 8. Then I've just moved the n down using our log laws, so n log of 2/3. So here we can say then, if we just rearrange to get n on its own, n equals minus 8 over log of 2/3, put the numbers in, and you should get an answer of about 45. So the neutron that comes out needs to have 45 collisions, in our case with carbon, and at that point its energy is suitable enough for it to be absorbed, because then it will become what we would say is a thermal neutron. So let's have a look in a little bit more detail about the moderator. As we know, it's transfer of kinetic energy from neutrons to them in collisions. Most effective if they're similar sized. So hydrogen would need less collisions, but need to consider the practical issues such as chemical stability. Common moderators are water and graphite, which contains carbon-12, like our calculation that we just did. Coolant. This is, yes, it's cooling down the reactor, but in many respects, the reason we want to cool down the reactor is to get the heat out, to heat our water up to produce steam, to make our turbine and generator spin. Common coolants, it's water in a pressurised water reactor like the picture we saw, carbon dioxide in an AGR, an advanced gas-cooled reactor. And note, because of this, in a pressurised water reactor, water can be the coolant and the moderator, so it can do both jobs. Control rods. In order to prevent a chain reaction, we need to control the amount of neutrons that are being taken into the fission reaction. So if we take them out, the fission reactions will slow down and eventually stop if we needed it to. So these are automatically adjusted to keep the number of neutrons in the fission reaction constant. One fission event causes one neutron to be released, which causes one fission. If you can have it as a step through, so you've always got one causing one, nothing goes out of control. The moment that you get one fission event producing 2 neutrons that produce 2 fission events, you end up with a chain reaction. If you want to make a bomb, then obviously a chain reaction is what you would do in a nuclear bomb, but for power stations we need a very controlled reaction. So pushing the control rods in reduces the number of neutrons, so reduces the rate of fission energy. A little bit of a safety note, these are normally held on electromagnets, so if the power goes off, the control rods are dropped straight into the reactor, so shutting it down as soon as it possibly can. A little mention of critical mass in the specification. The critical mass, the idea of critical mass, is the smallest amount of material that will sustain a nuclear chain reaction. And why this is because some neutrons obviously escape. So the neutrons that escape from fissile material without being absorbed don't go on to cause any other fission reactions. If they're absorbed, then they obviously do, but the ones that don't take part. And so the critical mass is the smallest amount of material that can keep a chain reaction going. The idea is, look at these pictures, this would be too small, this would be about right, so you've got a self-sustaining critical mass reached. Now obviously this is shape dependent, because if you got a lump of uranium and rolled it out flat in a big long flat sheet, then obviously it won't keep fission going as well as if it was a sphere. Spheres are really good because they've got the lowest surface area to mass ratio. It's normally quoted with a mass and diameter as the shape of a sphere, and some things I found just off the internet here researching it. Uranium-235, its critical mass is 15 kilograms, and that's a 17 centimeter diameter sphere, whereas plutonium's 10 kilograms for a 9.9. So you can see plutonium is certainly more fissile than uranium is. Last little bit, safety. The specification for AQA, you need to have an understanding of what we've talked about today. So the reactor, it's made of thick steel vessel, it's got concrete walls, the emergency shutdown will insert the control rods. Nothing's handled on site or by humans, everything's handled remotely. So robots are used to a high level in these plants. Remember as well that the fuel isn't as dangerous as the spent fuel. So the spent fuel, the products of the fission reaction are far more radioactive than the uranium itself. The future of nuclear, advantages of fusion, obviously if we can get fusion online it would be a world changing. The future of nuclear at the minute, it seems as though we've got no choice, the main reason being it's zero carbon, although it has got other problems with it. The big issues are, what about the waste? And obviously, what about disasters? They don't happen very often, but when they do, they are awful. But dealing with the waste, the specification just gets you to understand that there's going to be different levels of waste. So high level of waste, this is going to be literally parts of the reactor. The spent fuel, what do we do with it at the minute? Well, we tend to just leave it alone. If we leave it alone, because very often the products have got very short half-lives, so after a few weeks or months, it's far less radioactive. Then we vitrify or sort of convert it into glass or contain it in glass. We bury it underground. We use geologically stable sites, but locations are an issue, transporting in an issue. Sellafield does a lot of reprocessing to try and get out some of the unused uranium and plutonium to use it again. Medium level, so this could be stuff that's not quite as radioactive but still very dangerous, sealed in drums, encased in concrete, and then we just bury it or seal it up in buildings. The idea here is that we need to keep an eye on this, not just for a few years, for many thousands of years. So this is a problem with nuclear power or fission power, is that it creates a problem that's going to last for a long time. Then there's loads of low level waste. Again, we seal it in drums. We often store it in purpose-built locations. What used to happen is contaminated water-based products would be diluted with seawater and dumped at sea. Obviously now that's illegal, but that gives you an idea of how things have changed in the early days of nuclear power. We didn't really handle the waste as well as we now do. So this is a big problem, and it's something that we're going to have to deal with until, as I say, we can crack fusion.